The last part of this lesson will cover 2 additional rules. So our goal is just going to be to focus on those. We want to calculate the probabilities of complex sentences that contain negations and ones that contain any kind of disjunction, not just ones that meet our condition of mutual exclusivity. Both of the rules we're going to cover today can actually be derived from the previous rules we've covered. And we're going to look at the negation rule's derivation now, but we won't look at the one for general disjunction. And I think the benefit of looking at the derivation is it does help illustrate the way that the probability formulas can interact with each other and the way they allow us to determine the truth values of more complex sentences. So here's how we get to our negation rule. We actually start with our simple disjunction rule. So we know that the probability of P or Q is the probability of P plus the probability of Q, as long as P and Q are mutually exclusive. We also know that any sentence and its negation are mutually exclusive. Remember, mutual exclusivity is our probability name for inconsistency from truth functional logic. So P and not P are mutually exclusive. If that's the case, the probability of P or not P is the probability of P plus the probability of not P. But we also looked at this example before. P or not P is a tautology. And we know that there's a rule for the probability of a tautology. It always equals 1. So the probability of P or not P equals 1. Well, we can combine the equality on this line with the equality on the previous line, and that gives us that the probability of P plus the probability of not P is equal to 1. And by doing some basic rearranging of this formula, we get that the probability of not P is 1 minus the probability of P. So that's our negation rule. The probability of a negation is 1 minus the probability of the sentence being negated. How does this rule make sense? Well, we can draw a circle around the circumstances that make the sentence P true. That's in our diagram there. And all of the other circumstances are ones that make not P true. So the circumstances that make not P true are all the ones in which P is not true. Alternatively, not P can only be true when P is false. So we know this is the way negation works. Now we need to determine what's the chance of negation being true. Well, if the box represents all the possible circumstances, the chance of the negation being true is the chance of falling within the part of the box outside of the circle in which P is true. That's where not P is true. And that's what we're trying to capture. Now let's look at an example of this rule. Every week, Akiko runs 3 days and does yoga 2 days, and never both on the same day. The other days of the week, she doesn't exercise. What's the chance that any day is a non-exercise day for Akiko? So this is an example that's going to ask us to use our new negation rule, but also some previous rules. First, we need to determine the chance that any day is an exercise day. So we'll call that statement E for Akiko exercises. Well, because that sentence is true in all the same circumstances as the sentence Akiko runs or does yoga, those 2 sentences are factually equivalent. And we're going to symbolize Akiko runs or does yoga as R or Y. So because we know from one of our earlier rules for equivalent sentences, the probability of E is equal to the probability of R or Y if they're equivalent, if they're true in all the same circumstances. And to get the probability of R or Y, we need to know the probability of R and the probability of Y. And those are given in the description of the example. So 3 out of 7 days Akiko runs, and 2 out of 7 she does yoga. So now we can determine the probability of R or Y by adding the probability of R to the probability of Y, and that's 5/7. That means we get the probability of E, because the probability of E is equal to the probability of R or Y. And we need the probability of E to get what we're interested in, the non-exercise days. So we need to know eventually the probability of not E. To get that, we finally need to use our formula for negation. That tells us that the probability of not E is 1 minus the probability of E, which is 1 minus 5/7 or 2/7. So the probability that Akiko doesn't exercise on a particular day is 2 out of 7. So far, all of the rules for probabilities of complex sentences have depended on the truth values of simple sentences. But with our next rule, that won't be the case anymore. I want to take this moment, though, to draw this contrast between truth functional logic and probability. So with truth functional logic, the truth value of complex sentences could always be built up from the truth values of the simple parts. And we could see that in the characteristic truth tables that define each connective. They tell us how that connective works no matter what the truth values of the connected sentences are. No matter how complex they were, as long as they had the right truth values, you could get the truth value of a sentence with that connective. For example, the truth value of P or Q depended only on the truth values of those disjuncts, P and Q. That was enough to get the truth value of the whole sentence. That won't be the case for probability, or the parallel won't. The difference is that the probabilities of complex sentences sometimes depend on the probabilities of other complex sentences. So our rule for simple disjunction was one where the probability of a complex sentence only depended on the probabilities of simple sentences, the probability of P and the probability of Q. But that only worked when P and Q were mutually exclusive statements. The general rules for disjunction and conjunction, however, will partly depend on the probabilities of complex sentences. And we're going to look at the general rule for disjunction now. So while our simple disjunction rule only applied when sentences were mutually exclusive, our general disjunction rule will apply anytime. Because it is possible to have the disjunction of compatible sentences, sentences that aren't mutually exclusive. So here's an example. Shelley likes persimmons or guavas. From that sentence, it's possible that she only likes persimmons. It's possible that she only likes guavas. But it's also possible that she likes both persimmons and guavas. All of those circumstances would be ones that make that statement true. We need a new rule that allows us to calculate the probability of disjunctions where the two disjuncts are compatible statements. And that's what our new rule does. For any two statements, P and Q, the probability of P or Q is equal to the probability of P plus the probability of Q. That part's familiar, but we need an extra term, minus the probability of P and Q. So note here that the general disjunction rule depends on the probability of the complex sentence P and Q. We need to somehow know that antecedently to be able to figure out the truth value of this disjunction. Now, as I mentioned before, in the text you can find a derivation of this general disjunction rule. And what it depends on is our knowledge of which sentences are equivalent, some information we've used in a previous example, and also which sentences are mutually exclusive. The derivation's kind of long, so instead I'm just going to motivate why this rule works in general. You may, however, find the derivation useful, again, to understand how these probability relations work and how these equations work. So, what does this general disjunction rule tell us, and why does it make sense? Well, since P and Q are not guaranteed to be mutually exclusive, there could be an overlap in the circumstances that make P true and the circumstances that make Q true. So we see that in the diagram. There's an overlap in the set of circumstances in the orange circle that make P true and the ones in the green circle that make Q true. P or Q is true as long as at least one of the disjuncts is true. That means it's also possible that P or Q is true when both disjuncts are true. And that's possible when the statements are mutually compatible instead of mutually exclusive. So this diagram, you can go back and contrast it with this diagram for our simple disjunction rule. Because they overlap, these sentences are not mutually exclusive. So if this is what we're looking at for our general disjunction rule, we can now calculate the probability of a disjunction. And what is the chance of P or Q being true? Well, again, the box represents all the possible circumstances, and we still want to know the chance of falling within at least one of those circles. The difference is that because the circumstances in the two circles overlap, we have to make sure we don't double count the overlap between the circumstances that make them true. That's how we get that additional term. Subtract the probability of P and Q. That's what that overlap is. And we can get back to our simple disjunction rule from this. If P and Q is mutually exclusive, then the overlap is 0, so that last term gets canceled out. Now let's look at a pretty straightforward example of this general disjunction rule. What's the probability that it is snowing or sleeting in New Brunswick? And let the probability that it's snowing be 0.2, the probability that it's sleeting be 0.5, and the probability that it's snowing and sleeting is 0.2. So again, we need this extra piece of information, the probability of this conjunction. And so far, we don't really have a way of determining the probability of this conjunction unless snowing and sleeting are independent. But it's not so clear that they would be. So here, we're just given this number directly. So since we're interested in the probability of it snowing or sleeting, we need a way of representing that statement. And we'll use N for it is snowing and L for it is sleeting. Snowing and sleeting are not mutually exclusive weather conditions. They can happen at the same time. That means we can't use our simple disjunction rule. We have to use our general disjunction rule. And we have all the numbers we need given to us. So we need the probability of N or L, and we have the probability of N, that it's snowing, that was 0.2. We have the probability of L, that it's sleeting, that was 0.05. And we have the probability of the conjunction, that it's snowing and sleeting. That's 0.02. So we add the first two, subtract the last, and get 0.23 as the probability that it's snowing or sleeting, where it's possible that it's doing both. And with that, you should now know the rules for determining the probabilities of statements of the following forms: tautologies, contradictions, pairs of statements that are equivalent, negated sentences, any disjunction, or that includes the special rule but isn't limited to it. And conjunctions when the conjuncts are independent. And you should also be able to combine these rules to determine the probabilities of sentences that combine these connectives. So, for example, if you had a disjunction where one of the disjuncts was a negated sentence, how would you determine the probability of that? In our next lesson, we're going to actually introduce the general conjunction rule that we haven't gotten to yet. But for that, we're going to first need to introduce the notion of conditional probability. So that's what's coming up.